Alrighty, folks, we'll get started here for Chapter 1, Lesson 3. Just a reminder, make sure you have your notes, whether that's printed out or just following along on loose leaf, because you'll want to be following along, actively engaging with the material. You'll get a lot more out of the lesson that way. All right, here we go. We're going to talk about non-uniform motion now a little bit more. So in order to talk about non-uniform motion, it's helpful to remind ourselves of uniform motion in the first place, what we've been talking about over the past few lessons here. So remember, uniform motion is motion in which an object travels at a constant velocity, right? Remember, velocity is about how fast you're going and in which direction. So if you have a constant velocity, it means you are not speeding up, you are not slowing down, and you are not changing direction, right? Just one constant velocity in a straight line. So today we're going to examine non-uniform motion, and you can probably piece together that if uniform motion is when you have a constant velocity, non-uniform motion is when you do not have a constant velocity. And whenever your velocity is changing, you are accelerating. Get used to that word. We're going to use it a lot, okay? So all it means to be accelerating is to have a velocity that is changing. So what are the ways that a velocity can change? Well, it could get faster or slower, so it could be undergoing a change in speed, right? Or it could be changing just its direction, right? It might still have a constant speed, but it's going in a different direction. If either of those things change, we say the object is accelerating, okay? Now, the object's acceleration is just the rate at which the object's velocity is changing as time goes on, right? So if an object is speeding up, slowing down, or changing direction, it is accelerating, right? And that's all acceleration is. It's sometimes an idea that trips students up a bit, okay? But all it's saying is how much is your velocity changing by each second. It's measured in meters per second, that's the velocity part, per second, right? So how much is your velocity in meters per second changing each second, okay? Now we simplify that a bit. Instead of saying meters per second, we say meters per second squared. And that's just because we can do some simplifications with these units here, right? We have meters over seconds being divided by seconds. Well, we know we can write that as meters per second. Yes, we're dividing it by seconds, but that's the same as multiplying by 1 over seconds, right? Dividing by seconds is the same as multiplying by 1 over seconds. The same way dividing by 2 is the same as multiplying by 1 over 2, right? Same idea. So if we look at this, meters over seconds times 1 over seconds gives us meters over seconds times seconds, seconds squared, right? So in acceleration, yes, we say meters per second squared, but when you're first getting used to the idea, I do find it a little more helpful to really think of it as a meter per second, right? Because it's how much is the velocity changing by each second, right? It tells us how an object's velocity in meters per second changes each second. That's its acceleration. Okay, so just like velocity was the rate at which displacement was changing, acceleration is just one layer deeper. It's the rate at which velocity is changing. Okay, and so we can see that if its velocity changes every second, well, then the displacement it's covering each second is also changing, right? If it went, 5 meters in the first second, maybe it's going to go 10 meters in that second because it's getting faster in that example, right? Or it could be going fewer meters in the next second because it's getting slower. So if the object is speeding up, getting faster, that just means that the object's velocity and the acceleration, right? So how fast it's moving and how fast it's moving is changing each second are in the same direction. So the object goes faster. So acceleration is a vector, right? If you are moving forward already and you're accelerating forward, that just means your velocity is getting, bigger and bigger in the forward direction. The acceleration's you can think of it as helping the velocity, so to speak. But it's also totally possible for an acceleration and a velocity to be in the opposite direction, and that's what is happening if you slow down. So your velocity is in one direction, but it's changing in the opposite direction. And so the object goes slower, right? You do this every time you brake. You're moving forwards, but you're actually accelerating backwards, right? Moving forwards, but your acceleration is changing to be less and less forwards, or in other words, more and more backwards, okay, until you come to a stop. So we sometimes refer to this specific situation as a deceleration. You will sometimes see that term used. I want to emphasize, a deceleration is an acceleration. It's just a specific type of acceleration where the change in velocity makes the object move slower. In other words, where the acceleration is in the opposite direction as the velocity already. Okay, but that's all an acceleration is. It's how much the velocity is changing by each second. So if the acceleration's in the same direction as the velocity to begin with, it gets faster. But if it's in the opposite direction that the velocity was in to begin with, it gets slower. So we're going to use an animation to take a look at some accelerations in a second. But before we do that, I do just want to take a second and let's just look a little bit at, a simple situation to get a feeling for what an acceleration is, okay? And then we'll do some visuals to go along with it. So it wants us to complete the table below for an object that is initially moving forwards at 2 meters per second. So that's the velocity it starts out with. But it accelerates backwards at 1 meter per second each second, or 1 meter per second squared, for 4 seconds. Okay, so non-uniform motion, velocity is changing, and it's accelerating backwards when it started out moving forwards. So remember, all this means is that its velocity is changing by 1 meter per second in the backwards direction each second. So acceleration is a vector. Okay, and we know when we're dealing with vectors and directions, we need to be careful about signs if we want to think about, math involved, which we do here. Okay, so I'm going to go ahead and define forwards as positive and backwards as negative. And so that means if our acceleration is backwards 1 meter per second each second, I'm going to call that, it's an acceleration of negative 1 meter per second squared. And so all that means is that every second, its velocity is going to change by negative 1 meter per second, right? So if we look here, they've started the table for us. When time first starts, it was moving forwards at 2 meters per second. So its velocity is forwards, that's positive. It's moving forwards at 2 meters per second. But each second that goes by, we now know that's going to change by negative 1 meter per second each second, right? So if it was initially moving at 2 meters per second forward, changes by negative 1, well, that's going to bring it to positive 1, right? 2 minus 1 brings us to a 1 meter per second. Notice it's still moving forward, right? Its velocity is still forward. So what's happening to it here? Right? It's getting slower, still moving forwards, but it is getting slower because it is its velocity is forwards, positive, but its acceleration is backwards, negative, right? Opposite signs on those velocities and acceleration. So the object's speed is decreasing. Okay, after another second, what will its velocity be? Right, it's going to change by another negative 1. That's what an acceleration of negative 1 meters per second squared means. So now it will actually be going 0. It's going to stop there. It's going to not be moving for a second, okay? But it continues to accelerate backwards. So after another second, right, what's its new velocity going to be? That's right, its velocity is actually now going to be negative 1 meter per second. Okay, so think about what's happened here, right? It's now, which way is it moving? Which way is its velocity? Right, its velocity is actually backwards. So to recap so far, it was moving forwards, got slower, came to a stop, and now it's actually turned around and it's going faster and faster in the backwards direction. If this acceleration of negative 1 meter per second each second continues, you can see that, a second later it'll be going negative 3 meters per second or 3 meters per second backwards, 4 meters per second backwards, 5 meters per second backwards, assuming this acceleration continues, okay? But that really is all an acceleration is. It's how much is your velocity changing by each second. So I want you to compare these two sections of the table here and use it with what we know from before, right? We said that if the velocity and the acceleration were in the same direction, the object goes faster. If they're in opposite, it goes slower, right? So look here. From the first couple seconds here, its velocity was positive. It was moving forwards. Well, the whole time it was accelerating backwards, right? And so sure enough, positive or forward velocity, but a negative acceleration, the object did get slower. Right? It went from +2 to +1 to 0. 2 meters per second forward, 1 meter per second forward, not moving forward, right? Opposite signs on those two vectors caused our object to get slower. But then look down here, right? It continued to accelerate in the negative direction like it was doing that whole 4 seconds, right? But because it's accelerated long enough, it's now actually moving backwards as well, right? So its velocity is negative, its acceleration is negative, and so our object now gets faster just in the negative direction, right? So it is moving faster and faster and faster, it's just doing it backwards. Okay, let's take a look at some visuals here now in the animation. Okay, so I'm just going to start out with a simple case here where he's starting out not moving. Okay, now it's just some quirks in the simulation. It's showing his velocity as, 0.043. It's starting at 0. It's just the way it's displaying. Okay, you can see he's not moving there. Now the acceleration, again, the simulation wouldn't let me get exactly 1 meter per second squared. So it's a little bit faster than 1 meter per second squared. But let's just call it, for the sake of, simplicity, we'll just say he's accelerating at +1 meter per second squared. You can see there it's actually 1.029. Okay, now what does that mean? It means that each second his velocity should be changing by +1 meter per second, right? So after 1 second, what we expect his velocity to be? +1 meter per second. After 2, +2 meters per second, right? I'm just going to press play here. We'll see what that looks like. So what did you notice, right? He wasn't moving, but because he was accelerating at +1 meter per second each second, he started moving to the right, and then he got faster and faster and faster, right? He starts moving after about 2 seconds. His velocity is now about 2 meters per second. After about 4 seconds, right, his velocity is a little above 4 seconds. His velocity is a little above 4 meters per second. And he just continues to get faster and faster and faster. In fact, if you keep your eye on the red velocity section there, look at the meters per second, you can see it's increasing roughly at the same rate the time is increasing because he's accelerating at 1 meter per second each second. I can put in the vectors here to show you too, right? Look, at first he's not moving, so that velocity vector, which should be red, no vector, he's not moving. His velocity is 0. He is accelerating though, right? And so he's got that green acceleration arrow there. Watch what happens as the simulation runs, right? That velocity vector continues to steadily grow at a rate of 1 meter per second each second. Okay, let's start off a slightly more complicated situation. So now he is already moving. Okay, I've paused time, that's why he's not, but you can see he's moving to the left there at a velocity of -2 meters per second. Okay, so he's already moving. Now, look at the acceleration in green. His acceleration is -2 meters per second squared. So what does that mean? Well, each second, his velocity should be changing by 2 meters per second in the negative direction. So I want you to think about that. 1 second from now, what should his velocity be? Well, it should be 2 more in the negatives, right? And then 2 more in the negatives the next second. I'm just going to press play, and you can think about what that actually looks like as he moves. There he goes. Okay, so what happened? Well, it looks like he got faster and faster, but backward, or to the left this time, right? This time in the negative direction. Well, that makes sense because his velocity was to the left and his acceleration was to the left. So he was just getting faster and faster to the left by 2 meters per second each second, right? If I press play, after 1 second, he started out at -2 meters per second. Now he's at -4. After 2 seconds, he went from -4 to -6 meters per second. After 3 seconds, whoops, I overshot it a bit. He went from -6 to -8, right? You see that? -2, -4, -6, -8. His velocity is just changing by the same amount each second. And that amount is what we would call his acceleration. I'll once again show it with the vector arrows drawn in. So in green is his acceleration of -2 meters per second each second. In red is his velocity, his initial velocity of -2. But look how it changes over time, right? Okay, and let's look at one more here. Okay, so again, time is paused. He's not, we're not showing him moving, but you can see he is initially, when we start looking, he's moving to the left at 4 meters per second, right? Or roughly as close as the simulation lets me show it. So negative 4 meters per second is his initial velocity. But look at his acceleration. It's positive 2 meters per second each second. So I want you to think about that. I want you to pause the video, make a prediction about what we're about to see before I press play on this, okay? And then we'll break it down together. So go ahead, pause, make a prediction about what this will look like. And I'm gonna press play now. Aha, look at that, right? I'm going to do it again with the vectors on so you can see the acceleration vector is in green. It's to the right at 2 meters per second each second. The velocity vector is to the left. It's starting out at 4 meters per second. Let's watch it again. Cool, right? So notice his acceleration vector never changed, right? The acceleration was a constant 2 meters per second squared. It's the velocity changing in the positive direction by 2 meters per second each second. So watch, if he starts out at negative 4 meters per second, but he's accelerating at positive 2 meters per second squared, then after 1 second, his velocity should be negative 2 meters per second. So he should still be moving to the left, but he'll have gotten slower, right? Sure enough. After 1 second, he's still moving to the left, but he's definitely getting slower and slower and slower. Look what happened at 2 seconds, right? He's accelerating at positive 2. So starting from negative 4 meters per second, he's going to go to negative 2 meters per second and then 0 meters per second. Sure enough, that's what we saw. He got slower and slower and slower, stopped, and now he continues to accelerate in the positive direction. So he's going to go from 0 meters per second to positive 2 meters per second, to positive 4 meters per second, to positive 6 meters per second, and on and on and on, right? So all that's happening there is that his velocity is changing by positive 2 meters per second each second. That takes him from a velocity of negative 4 meters per second to negative 2 meters per second to 0 meters per second to positive 2 to positive 4 to positive 6. And he keeps going like that until his acceleration changes again. So recall the equation from Science 10 for acceleration, right? Now that we've kind of gotten a chance to dig in and explore it a bit. This is actually all still Science 10 review, okay? But the equation kind of tells you what the acceleration is, right? I mean, that's what all equations really do at the end of the day. It shows us that it's how much did your velocity change by divided by how long did it take you to make that change in velocity. And what that gives you is your change in velocity per second or your acceleration. Okay, so finding that on the formula sheet, you can see here that your average acceleration each second is just going to be how much your velocity changed divided by how long it took you. Side note here as well, if you're keeping track of those physics principles on the back of your formula sheet, remember these are really just here so that ultimately we can ask you on a question, you know, which physics principle did you use? What were you actually thinking about? What knowledge were you applying, right? It helps us understand, you know, get a look at how your brain's really applying your knowledge. Okay, you'll see we're now kind of dealing with physics principle number 1 here, accelerated motion. You can see that that says the net force is not 0. We're going to talk about that idea a lot in chapter 3, but for now, just focusing on the idea of this is non-uniform motion. Okay, so there is the equation for calculating an acceleration, or, you know, calculating a change in velocity or a change in time when you have the acceleration, but that's what we're going to do. Okay. So, one more thing I'll mention here. Remember, a change in anything, to find a change in velocity, you'll just take the final velocity and subtract the initial velocity, right? So it's not written out that way on your formula sheet, okay? But it essentially is, because you know that a change in anything can be found with final minus initial, right? Where'd you end up? Minus where you started. That tells you how much you changed your velocity by, okay? Very important to note that in here, there are implicitly 2 velocities, right? It's not just a velocity, it's the difference between 2 velocities, the final velocity and initial velocity. Okay, so try this out. Pause the video here. What you're looking at is just a bunch of, picture it like it's like someone took a snapshot and then put them all together of different objects in motion. And it's asking you, which of these objects are undergoing uniform motion and which ones are undergoing non-uniform motion if this is what each object looked like after each 1 second snapshot. Go ahead, try that out, and then we'll talk about it together. Okay, so what'd you get for this car? Well, we can see here this car, right? In the first second, it looks like it went 2 meters, but then in the next second, it went 6 meters, right? 2 meters during this first second, then 6 meters, then suddenly from 8 all the way to 18, that's 10 meters. So is this uniform motion? No, right? It can't be. It's changing the displacement that it covers each second. Well, that means its velocity is changing, right? This car is getting faster and faster. Okay, what about this golf ball? 1 second it went 1 meter. The next second it went another 1 meter to get to 2. Next second, another 1 meter. 1 meter, 1 meter. Yeah, this is uniform motion, right? This is uniform. Okay, it's going the same distance each second, and therefore it has a constant velocity. How about this ATV? Uniform or non-uniform? Right, this would be non-uniform, right? Slowing down is an acceleration, right? It's a change in velocity. And so it covered 13.5 meters in the first second, and then much shorter distance in the next second, shorter distance, shorter distance, shorter distance. This thing's velocity is definitely changing. This is non-uniform motion, okay? And then finally, what about this plane? Doesn't give you the numbers, but from the visual here, right? Well, if it went, that distance in the first hour, that distance in the second hour, that distance in the third hour, looks like they're about the same, right? And so this looks like uniform motion. It's covering the same displacement each hour. Therefore, its velocity throughout that time must have been constant. Otherwise, it would have been changing the displacement that it was covering from 1 hour into the next hour. Okay, so soon in the next lesson, we're going to cover algebraic analysis, which just means analysis using formulas of an accelerating object's motion, okay, analyzing it with math, though this is also math, it's just graph math, okay? But we're going to introduce the concept by looking at graphical analysis of non-uniform motion in this lesson, okay? Next lesson, we'll pull out some formulas, and next lesson will actually be the first time we do something that is new to Physics 20 and you didn't cover in Science 10. So that's another reason we're starting with the graphical analysis, is that you've actually already analyzed graphs for non-uniform motion in Science 10. So this is a little bit more review, okay? So it wants us to first, and I'm actually just going to go with this, we're going to just describe the slope, okay? We never want to fully put our physics brains away, but let's just really, to emphasize the point we're about to make here, let's really just look at slope and not think about this being an object moving or anything, but just like, we have a graph and we want to think about its slope. So for object A here, what are some words you could use to describe this slope? Well, how about, is it positive, negative, zero, undefined, right? This is a positive slope. Very good. It rises to the right, so it's a positive slope. And anything else we could use to describe this slope? Is it changing or is it a constant slope, right? It's a constant slope, right? It's always the same steepness, okay? Every time it, runs a certain amount, it always rises the same amount. If we think about drawing little triangles in here, right? Every time I run 3, it looks like I'm going up the same amount. If I was climbing this hill, it's not like it's getting steeper and steeper and steeper. It's the same steepness the whole time. So this is a constant slope. Okay, now looking at the green one here, I know it's a little weird, okay, but let's describe the slope to the best of our ability, right? I know it's not a line, so it's kind of weird to even talk about its slope. But I mean, we can think about, all right, well, it is rising to the right. So this is like, it's a positive slope, but it's definitely not constant, right? Like, for example, down here, if I run 2, I only rise that much, right? Whereas just for the next 2, if I run those 2, I rise a little bit more. And then if I run 2 here, I rise more. Right? I'm running the same amount, but my rise is getting more and more. In fact, I can't even see the rise for that one. It goes off the graph, right? So this is not a constant slope. It seems to be increasing. If you imagine walking along this hill, right? It's getting steeper and steeper and steeper. This hill is getting harder and harder to climb. So we could say our slope is getting steeper or larger, right? And it's in the positive direction. The rise over run is getting bigger and bigger and bigger, though it always remains positive. Okay, now let's switch those physics brains fully back on and think about what is happening to these objects' motion as it asks us to describe their velocity. Now notice we have a displacement as a function of time graph. So displacement is on our y-axis, time is on our x-axis. And that means that what a rise really represents on this graph is a change in the object's displacement, right? As we did in the previous lessons, okay? So for example, after 4 seconds, it's gone about 3 meters to the east, right? Okay, and a run is a change in time, right? So if we take a look here, okay, if we think about this in terms of velocity, what's happening to this object? Well, we kind of just said it, right? After 4 seconds, it runs 4 seconds, and after those 4 seconds, our object has moved to 3 meters east, right? What happens in the next 4 seconds? Well, it now has gone from that 3 meters east to that 6 meters east, right? Next 4 seconds, it's gone from 6 meters east of where it started to 9 meters east of where it started. So every 4 second interval, this thing is just moving 3 meters to the east, right? So it has, if we wanted to describe the velocity, okay, east is being defined as positive, so it has a positive velocity because we just saw that it's moving to the east. And we also see that it has a constant velocity, right? Every 4 second interval, it was covering the same displacement. Every 4 seconds, it's going to go another 3 meters, right? Hey, we actually kind of already knew that, didn't we? We knew this connection could be made because the slope of a displacement time graph is telling us the object's velocity, right? That's not just some magical thing, right? We know that that has to be true because velocity is defined as the change in displacement over the change in time, which for this graph, that means it's a rise over a run. Displacement over time, that's rise over run, slope. Okay, now that doesn't change even for something like B here, where we have a slope that's changing, okay? So if we take a look here, how could we describe this thing's velocity? Well, I mean, we already kind of talked about it, right? In the first 4 seconds, it only goes about that far, right? Not quite 1 meter to the east. But in the next 4 seconds, right, it suddenly goes almost another 3 full meters roughly to the east, right? Same amount of time as the first interval we looked at, but it's gone much further in that same amount of time, okay? Next 4 seconds, oh my goodness, it's already gone so far that we can't even, whoops, wrong color. It's gone so far that we can't even see where it is on our graph, right? So how would you describe this thing's velocity? Right, it's getting faster and faster and faster. Hey, we said the slope was increasing. We know the slope of a dt graph is velocity, and sure enough, its velocity is increasing. We're getting a larger and larger velocity in the positive direction. Look, we said positive slope and getting bigger, getting more and more positive, right? That's exactly how we would describe this velocity. It's always moving in the positive direction, but it's getting faster and faster and faster at moving in the positive direction. So notice how much these two mirror each other, right? It's got a positive velocity that's increasing, right? Just like we saw for the slope, okay? And again, that's not just a coincidence. That has to be true because of this fact here. Okay, so it asks us then directly on the graph, add a curve for a stationary object. What does stationary mean? It means it's not moving at all. Okay, so that doesn't necessarily mean it's at a displacement of 0, right? It could be sitting 4 meters east of where these guys are, right? And just not moving. So I'm going to do that just honestly mainly because I think it'll show up a bit better. So I'll do it in purple here, okay? Let's just say that. Let's say it starts 4 meters east of where those things started. What does it look like if it's not moving? 1 second later, where will it be? Right, it'll still be 4 meters east because it's not moving. Its velocity is 0. It's a stationary object, right? And that'll continue on and on and on and on. So it's going to look something like that. There's our stationary object's displacement time graph. Now, look at the connections here, right? What's the slope of a line like this? How much is it rising? No matter how far we run, how much does it rise? 0, right? It never rises. 4 minus 4 is still going to be 0 to find the rise. Hey, what's the velocity of a stationary object? 0. The slope of a displacement time graph tells us the velocity. This thing has a slope of 0, so it has a velocity of 0 like we would expect for a stationary object. So I can't emphasize this enough, right? Graphical analysis, honestly, a very simple process, okay? As long as you understand that the core idea is about being able to connect the graph, either its slope, its area, its intercept, to an equation. And that's not a guessing game. The equation tells you, right? I knew that the velocity was the slope because the equation shows me. This is rise, this is run. Rise, run. So velocity will be the slope. Rise divided by run. Okay? So it asks, why did the slope of a displacement time graph represent the object's velocity, right? That's not just something we have to memorize. It's because of that, what we wrote there. If we have a displacement versus time graph, well, the slope of that is rise over run, which is going to be a change in displacement over a change in time, which is just the definition of velocity. How much does displacement change each second? All right, so now it's asking us to take this idea and apply it to a velocity time graph, right? It's asking us, what would the slope of a velocity time graph represent? And here's the key thing, right? Why? Is it something to guess or memorize? No, right? We can figure out why. So what would the slope be for this graph? Let's write it out. Well, slope is always just rise over run, right? Rise is how much our y variable changes by between 2 points. Well, our y variable here is velocity. So the slope of this graph would be a change in velocity, okay, divided by run. Run is how much the x variable changed, so that's a change in time. Change in velocity divided by change in time. What is that? If we're not sure, we can always go to our formula sheet and see, right? But hey, a change in velocity divided by a change in time, that's the object's acceleration, right? That's the definition of its acceleration. And so there we go, right? We've shown it. It's not just because, right? It's not just something to memorize. We can see, hopefully, why the slope of a velocity as a function of time graph would represent its acceleration, okay? So we're going to look a lot more at VT graphs. We looked at some in the previous lesson, but now we're going to start doing it a lot more with non-uniform motion, okay? Now, super important thing to remember, okay? I mean, in general, always, but with VT graphs, velocity is now what's on our y-axis. We're not looking at DT graphs anymore, okay? I mean, we are going to still look at them, but important to always be on your toes. And first things first, recognize what is on your graph, what's on its y-axis, okay? Because the number one mistake students make here is they mix up what the y value tells them with what the slope tells them. And that is honestly because they are still thinking of them as DT graphs. So you always got to ask yourself, both of these graphs are useful, but different characteristics of them tell you about different things because the graph is showing you different things, right? It's showing you about a different variable anyway, okay? So remember, the y value on a velocity time graph, that just is the object's velocity at that time, right? If this is, if we have a point on our graph that's at 5, that just means the object is moving at 5 meters per second, right? At that point in time. Later on, if its y value is 6, well, at that time, it was moving at 6 meters per second. It's just directly the y value will tell us the object's velocity because that's what's on our y-axis, the object's velocity, okay? Students often will go ahead and just find the slope, but that's because they're thinking they're looking at a DT graph, right? The slope of this gives us the velocity because the slope of this is going to give us the change in displacement over the change in time. If we're given a VT graph and asked to find the velocity at a certain time, we just need to read what the velocity is off the y-axis. Which leads me to the next point here, right? The slope of a VT graph tells you how that velocity is changing each second. Rise over run. Rise would be change in velocity. Run would be change in time, okay? In other words, the acceleration. So I can't tell you how many times I've seen students with a velocity time graph and they're asked to find the velocity at a certain time and they calculate the slope, right? But now they're calculating the acceleration. They actually did more than they had to. If you're asked to find the velocity with a graph that has velocity on the y-axis, you just need to read the y value at the point you're interested in. Okay, so let's go ahead and try out an example here. So using graphical analysis, determine the acceleration of the object whose motion is depicted in the graph below. So like always with graphical analysis, we want to make sure we understand what's on each axis. Here we have velocity on the y-axis and time on the x-axis. So here's what we're dealing with. Just like solving any question, you're going to have given variables and required variables, right? In this case, it's just that our givens are given to us on a graph. So we are given velocity, we are given time, and we are asked to find acceleration. So like we'd always do, we'd say, okay, well, what equation relates those variables? So we can go to our formula sheet and we can see that, aha, if I could find the change in velocity and the time it took to go through that change, then this equation can help me out. Now to show the graphical analysis piece, we start by writing our equation, right? It's already solved for what we want to find, so life's good. Acceleration is change in velocity over change in time. We look at that, we look at our graph, and we say, hey, we're dividing y by x, right? We have a rise over a run, so we are going to find the slope. This is the crucial step, and it needs to be shown for graphical analysis work, okay? The reason being, graphical analysis always comes down to finding a slope, an area, or an intercept, right? So I need to be able to tell the difference between the student who understands why they're finding the slope and the student who just kind of flipped a coin and said, I don't know, sometimes we found slope, maybe it'll be slope this time, okay? So important to show that step there. But once we've done it, all that's left to do is pick two good points, find the rise and the run between them, and then divide to get the slope. So let's look at our graph here. We want to pick nice, easy points where it's easy to read off and we don't have to do any estimating. We've got lots to choose from here. How about this one and this one? So between these 2 points, it looks like it runs from 2 to 4. So our run is going to be always final minus initial. 4 seconds minus 2 seconds. Our run is 2 seconds. And while those 2 seconds were going by, it looks like the velocity rose from 2 to 4 as well. So our rise, we ended up at 4 meters per second. We started at 2 meters per second. So our rise is positive 2 meters per second. So we've just shown that we can just find the slope, the rise, and the run. Well, the rise is 2 meters per second. When it ran, 2 seconds, and so we get that our acceleration is going to be positive 1 meters per second each second, or positive 1 meter per second squared. They didn't specify a direction on the y-axis here, so the best we can do is just have the right sign, right? We can just say it's in the positive direction. And there we go. We just used graphical analysis to determine the acceleration of this object. Okay. So looking at this next example here, we're going to sketch displacement as a function of time graphs and velocity as a function of time graphs for some scenarios. So it looks like we've got kind of, a multi-part story, so to speak, where we're going to be describing the motion of an object graphically with displacement versus time and velocity versus time. So where it is as time goes on, and then also how fast it's moving and in which direction as time goes on. Okay. Tells us to assume the positive direction is north. Okay, so that means on our y-axis here, any northward displacements or any velocities where it's moving north are going to be on the positive y-axis, and therefore anything to do with south is going to be down here on our negative y-axis. It also says to assume that any accelerations are uniform. Okay, so let's touch on that idea of a uniform acceleration. That's actually the most complicated motion for the most part we'll deal with in Physics 20. So be careful, don't mix up uniform acceleration with uniform motion. Uniform means the same thing in both. Uniform means unchanging, okay? But a uniform acceleration means it is accelerating, but it's not changing how it's accelerating, right? So that means, yes, its velocity is changing, but it's not changing how it's changing. Right? And that's, like I said, the most complex motion we'll deal with in Physics 20. We will see situations where, the object is accelerating, its velocity is changing, but it will always be changing by the same amount. Okay? Unless we're looking at a graph where we've got different things going on at different times. But in terms of calculations, the accelerations will be uniform. So the accelerations won't change, at least on the section we're interested in. Okay, we're going to use the driveway as the reference point for all displacements. In other words, that just means we're going to define the driveway as a displacement of 0. All other displacements will be referenced back to the driveway. Okay, let's go ahead and try part 1 here. A car sits stationary in a driveway. All right, so let's think about if the car is just sitting stationary in the driveway, stationary meaning not moving, well, as time goes on, right, for this motion, how is its displacement from the driveway going to be changing? Well, it's not, right? Where's it going to start at? It's in the driveway, so it's going to start at a displacement of 0, right? And if it's just sitting stationary in the driveway, well, as time goes on, it continues to just sit stationary in the driveway, right? Perfect. Okay, now let's look at the velocity as a function of time graph. Okay, now remember, we're not talking about where it is anymore. We're talking about how fast it's going. That's what's on our y-axis, right? It's velocity, not its position. Okay, but in this case, if it's stationary, what's its velocity? Right? If it's stationary, its velocity is 0. And if it's just sitting there as time goes on, well, its velocity will continue to be 0. Whoa, I didn't draw a very good line there, but hopefully you get the right idea. Okay, so that one maybe not the most exciting. Okay, but still interesting. It's showing us as time goes on, it's at a displacement of 0, and it sits there, right? It also has a velocity of 0 because it's not moving, and it just continues to do that for a little bit because it's sitting there. All right, let's look at the next thing, the next stage here where it actually does start to move. All right, so now the car begins to move north, picking up speed. Okay, so definitely when we look at our displacement time graph, it's going to start moving away from the 0 position, right? And it's moving north, which we're defining as positive. So we know that it needs to go up on the y-axis, okay? But we've got to think about how is it going to go up, right? So if it's picking up speed, well, that means it's getting faster and faster and faster, right? Which I want you to think about, what does that mean for the displacement it covers in each second compared to the previous second? If it's getting faster and faster, you know, how will the displacement that it covers in second number 2 compare to the displacement it covered in second number 1? Well, that displacement should be getting larger and larger, right? If it's getting faster and faster, it's covering more and more ground as time goes on. So we need to think about what that looks like on a displacement time graph. I'm going to just draw 3 options and to give you something to think about, okay? Only one of these is correct. So there, I drew 3 different possible shapes. Only one of those is correct. Try pausing the video now and see if you can, first of all, identify the correct shape, but also give a little bit of a justification of why, right? Why do you think that's the correct shape? And if you need a little help, I'll also ask you to think about, remember what we said about, displacement time graphs and slope and how that relates to the velocity, right? We know it's getting faster. What should that look like in terms of the slope of our graph as time goes on? Okay, so pause the video, think about that, okay, come up with your answer. But now we'll take a look at each of them individually, right? We want it to get faster and faster. So let's look at option 1 first. Is this showing it getting faster and faster? Well, okay. If it's getting faster and faster, like we said, it should be going further and further with each second that goes by, right? So let's just say, that's 1 second. Okay, in that second, it went that far, right? Here's another second. Now it's only going, a little bit less far. Here's another second, even less far now. Here's another second, less far, another second, and we can kind of see what's happening here, right? It's actually covering a shorter and shorter distance as time goes on, right? It is, even though these all represent 1 second, it's not going as far in each of those 1 second intervals. It is not rising as much for the same run as time goes on. So is this thing going faster and faster? No, it's actually going slower and slower, right? Okay, now pause and think about what the slope to here, right? Whoops, I don't mean to erase that, right? Take a second to think about the slope. How would you describe this slope? Is it getting steeper or less steep? It's getting less steep, right? And we know that the slope of a displacement time graph is the velocity. So sure enough, the slope is getting smaller, right? And that means the velocity is getting smaller. So it can't be option 1. That's definitely wrong. So let's look at option 2, right? Now again, this is how would you describe this slope? It's constant and it's positive, right? Well, that means since it's a dt graph, this object would have a constant positive velocity. But we know that it doesn't have a constant velocity. It's supposed to be speeding up, right? So right away we could say, okay, it's not 2 for that reason. But I mean, if we really want to dive in, look, every time we run 1 second, it's always rising the same amount, right? For every second that goes by, it covers the same displacement. So this object depicted by graph 2 is not speeding up. It's actually just going at a constant speed. So that's not quite right for this either. Which leaves us with option 3 by process of elimination, but let's make the connections to see why it's option 3, right? Hopefully you took some time to explain that yourself as well, right? Well, first of all, how would you describe this slope? It's increasing, right? It's getting steeper as time goes on, right? And we know that it's supposed to be getting faster. Well, the slope of a dt graph represents velocity, so a larger slope means a faster velocity. It's also a positive slope, right? It's increasing and it's getting more positive. Well, that's good because we know it's supposed to be moving north and moving north faster and faster. So we should see a slope that's positive, but getting bigger and bigger in the positive direction as time goes on, okay? A bigger and more positive slope. We can also take a look at the rises and the runs here, right? If I run 1 second here, I only go that far. But in the next second, I go a bit further. And in the next second, I cover more ground even. And in the next second, now look how far I'm going, right? By the time I get up here, I'm covering quite a large distance in just 1 second compared to what I was back here, right? So we can see that sure enough, it's covering a greater and greater displacement each second. In other words, it's going faster and faster. All right, so now let's look at think about what this needs to look like for our velocity time graph, right? Now again, it's picking up speed. So first thing to ask ourselves, is the velocity changing? Should we be moving on the y-axis, right? Well, yeah, it is. It's getting faster and faster, right? So now on our y-axis is the velocity. So we know we want to be going up on the y-axis as time goes on, and up because it's getting in faster and faster north, right? So anything up here represents moving north. We want to be getting faster and faster in the north direction, okay? Now, this is where that thing, any accelerations are uniform, comes in. So it is going to be getting faster and faster, but it's going to be doing it by the same amount each second, right? Its velocity is changing, but it's always changing by the same amount as time goes on, at least for this interval here. Okay, perfect. Oh, other thing, it starts at 0 because we know the car's not moving, right? One more connection to make back to our displacement time graph. Look, this starts with a slope of 0, right? Because it wasn't moving. So the velocity should be 0, and the slope of this graph would tell us our velocity. That's also something to notice here as well. Look how you would describe the slope of this and how that relates to the y value of this graph, right? A slope that starts at a slope of 0 becomes a positive slope that gets steeper and steeper. Well, here for our y value, it starts at 0, then becomes a positive y value that gets larger and larger, right? The y value of this is just doing what the slope of this was doing. Makes sense because the slope of this graph would be the velocity, and that's what's on the y-axis of this graph. All right, so now the car has reached the speed limit and it moves with uniform motion. Okay, so it is moving. Okay, so as we think about our displacement time graph here, right, its displacement should be changing because it's in motion, right? So we are going to move on the y-axis here, okay? But with uniform motion, what does that look like on a displacement time graph? Notice I'm not starting at 0 because we're no longer in the driveway, right? We are away from what we've defined as 0. Okay, but it's continuing to move north. It's just doing it by the same amount each second. It has a constant velocity, right? Once again, look at that. Constant positive slope. Well, it has a constant positive velocity because it's moving with uniform motion. Constant velocity. All right. Now, if we want to show its velocity as time goes on with velocity on the y-axis, remember, we got to think, okay, we're now talking about how fast it's going with our y values. Well, if it's moving with uniform motion, okay, first thing I'll ask you, is its velocity 0? No, Right, exactly. It's moving north at some constant positive velocity. So we'll say its velocity's up here. But is that velocity changing as time goes on? No, right? I mean, say it's moving at, 50 kilometers per hour north. Well, if it's uniform motion, then 1 second later, it should still be moving at 50 kilometers per hour north. And a second later, the same thing, right? So this is showing that it is moving. It does have a velocity, right? That velocity is just not changing, right? And once again, notice the connection here. The slope of this is constant and positive. The y value here, which is the velocity, is a constant and positive y value, right? If this is 50, it just stays at 50, for example. Okay. All right. Okay, so now things get a little more complicated. The car approaches its destination. It slows down and it parks. Okay, so we got some stuff to think about here. Again, still not going to start the graph at 0 because it's away from the driveway, right? It's somewhere north of the driveway. Okay, but we need to think about what does it mean for it to slow down in terms of the displacement it's covering each second. We already kind of talked about this up here, right? So it needs to be going as, for each consecutive run, it needs to be rising less and less and less because it's not going as far in each passing second as it did in the previous second, right? So again, I'll draw 3. You tell me which one and why. Okay, I know we talked about it up here, but pause the video, choose one, and give your logic as to why that is the correct one. Right? So it should be option 1, because again, for each second we run, we can see that it's rising not as far. In other words, right, it's not covering as much displacement in the next second as it did in the previous second, which is just a fancy way of saying it's going slower, right? Option 2 shows that it's moving north with a constant velocity, right? And option 3 actually shows that it's getting faster, right? It's the slope is getting steeper and steeper, okay? This one, option 1, has a slope that's getting less and less steep. And we know that the slope of a dt graph gives us the velocity, right? So since the slope is getting steeper or less steep and less steep, the velocity is getting smaller and smaller. Another thing to notice, what's the slope at the end there, right? It looks pretty flat. So the slope of a flat line is 0. Well, the final velocity should be 0, right? Because it parks. So since the slope of this graph, displacement time graph, tells us the velocity, right? We end up with a slope of 0. That means it ends with a velocity of 0. That's showing us the right thing. Now hold on to that thought as we move on to our velocity time graph, right? What is the final velocity? Well, it should be 0, right? Now on a velocity time graph, that means the final y value, right? Our final velocity needs to be 0, right? So we know that our graph has to end up here, right? With a velocity of 0 for this scenario, okay? But the question becomes now, okay, so how does it get there? Where do we start, right? Well, it was moving. We know that it was moving north. So it was moving north. It had a positive velocity, right? Again, just to put a number in, maybe it was moving 50 kilometers per hour north. And then as time went on, it got slower and slower and slower, approaching 0 by the end when it parked, right? So the velocity started at some positive value, decreased to 0 because it came to a stop, right? This is showing how fast it was moving as time went on, not where it was, how fast it was moving. And again, look at the connections here, right? Our slope is positive and decreasing, right? It's positive and it's becoming less and less steep, okay? We'll look at our velocity. It's a positive y value that gets smaller and smaller and smaller until it hits 0. A slope that was positive and decreased to 0, a y value that was positive and decreased to 0. Look at all those connections. It's fun, huh? I like these. It's like a little puzzle in your brain that you kind of work out, a visual storytelling. Okay, let's move to the next one. So now the car remains stationary in a parking lot. Okay, nothing too complex here, right? If it's stationary, it's going to stay in the same place. However, what's different than option 1 or stage 1 here, right? It's no longer in the driveway. So it is staying stationary, but it's not at our displacement of 0, right? It's wherever the grocery store is, however far north that is from where it started. So as time goes on, for this section of our journey, it's just going to stay at that displacement, away from our home, but not changing. And if it's remaining stationary, what's its velocity? 0, right? How is that changing if it's remaining stationary? It's not. Its velocity is staying at 0, right? Once again, look at the connection here. What's the slope of this line? 0. What does the slope of a displacement time graph tell us? The velocity, right? Sure enough, the y value here is 0. Slope of 0, y value of 0 on this graph, right? And again, remember, this is telling us how fast it's moving, not where it is, right? This one tells us where it is, okay? Common student mistake on this one would be to say, oh, but it's not at home, right? But you're not talking about where it is here. You're talking about how fast it's moving. So if you were to draw something like this, you'd be saying it's moving very fast, right? It's got a velocity that's not 0, so it's moving, right? That's not what we want. Okay, so now the car begins to return back the way it came, picking up speed. Okay, so a little bit tricky to think about these at first, but let's just start, always when sketching a graph, a good idea to say is, where does this graph start? Okay, well, we know it's somewhere north of where it began, so it's somewhere up here to start out with. Now we just need to think about how that's going to change over time. Well, it returns back the way it came, okay? So that means it's heading back towards, 0, right? Heading back towards the driveway. So we know we got to go down on the y-axis. It's now moving south, okay? So it's going to end up, somewhere over here. It's going to be closer to the house by the time this interval ends, okay? But it's picking up speed. So it's getting faster and faster, okay? So we need to think about what the slope of this is going to look like as time goes on. Once again, I'm going to draw 3 options. I want you to think about which one shows it getting faster and faster back towards the home. Pause the video, choose one of those, and justify your response. So let's think about this now, okay? It needs to be getting faster and faster to the south, right? Back towards home. So each second that goes by, it should be getting further and further towards the south, right? It should be covering a greater southward distance. So if you look at option 1, 1 second goes by, it goes a little bit towards the south, right? It runs 1 second, it rises down towards the south, runs 1 second, rises a little further, runs 1 second, rises even further. I didn't do the best job sketching that, right? It should probably look more like that shape, okay? But you can see, sure enough, right, as time goes on, this is covering a greater and greater displacement. It's just doing it to the south, right, in the negative direction, okay? So that actually sounds like a pretty good option. Let's explore options 2 and 3 and see why maybe they don't work. So option 2 looked like this. Now this thing is moving to the south, but how is it doing it? It's doing it at a constant velocity, right? It's always rising the same amount for each run. So that's not right. We want it to be getting faster and faster to the south. And then option 3 looked something like this, right? This thing is changing its velocity, but it's actually getting slower and slower, right? At first, for that 1 second, it went pretty far south on the y-axis, right? But then in the next second, not as far. Next second, not as far. Not as far, not as far, right? So this thing is constantly moving south, but it's always doing it slower and slower, which is not what we want. We want it to be getting faster and faster, right? Look at the slope of this thing. How would you describe this slope? This always has a negative slope, but it's getting less and less steep, right? It ends at a slope of 0. So this would, again, connecting it to velocity, it has a negative velocity, but that velocity is getting smaller and smaller until it reaches 0. That's not what we want. This thing would be moving very fast to the south at the beginning and then not moving south at all at the end, okay? So we did want option 1. This one here. This shows a negative slope that gets steeper and steeper and steeper, right? Starts with a slope of 0, and then that slope gets negative. Remember, that's a negative slope, falls to the right, okay? And it gets steeper and steeper and steeper. That indicates a negative velocity that gets larger and larger and larger, right? A bigger and bigger negative velocity. And once again, right, run that far, we rise only that far. But in the next second, we rise a little bit further, a little bit further, a little bit further. We can tell that we're covering a greater and greater negative displacement each second, which means it's getting faster and faster in the negative direction. That's what we want. Now hold on to that thought for our velocity time graph. Okay, we just said a slope that starts at 0 and gets more and more negative. Well, we know the slope of this tells us the velocity, right? So it should be starting from a velocity of 0 and now going down into the negatives. So this object is getting faster and faster. It's just doing it in the negative direction, right? And sure enough, again, right, it started not moving and then it got faster and faster in the negative direction. So it was going 0, maybe it finishes going at negative 50 kilometers per hour or 50 kilometers per hour to the south, okay? And I know I sound like a broken record, but it's an important connection to make, right? Once again, look at how the slope of this graph tells us about the y value of this graph, right? A slope that starts at 0 and gets larger and larger in the negative direction, right? It becomes more and more of a negative slope. Well, a y value that starts at 0 and becomes more and more of a negative y value. The y value of this is just showing us what the slope of this did. And again, that makes sense because the slope of a displacement time graph is the object's velocity at that moment. All right, we're getting close to home. The car reaches the speed limit and moves with uniform motion. Okay, so again, the displacement is changing. We're not home yet though. It's not starting from 0, okay? We're getting closer to home, so we know we're gonna end up closer to 0 on the y-axis, okay? And if we do it with uniform motion, we know that means we're covering the same displacement each second. Oh, I did a really bad job of drawing that as a straight line. Still not great. That's supposed to be a straight line, okay? So a constant negative slope, getting closer and closer to home, but doing it by the same amount each second in terms of its displacement change. All right, now think about that for velocity, right? It is always moving home, so it's always got a positive or negative velocity. Negative velocity, right? It's headed south, okay? Now, is that velocity changing? No, because it's uniform motion. So a constant negative velocity, right? Constant negative slope here tells us that our velocity is a constant negative value. Okay, and finally, the car returns home. So now our car slows down and parks in the driveway once again. Okay, so where do we end up in terms of displacement? Yeah, we know we end up at 0, right? We start somewhere north of the house still, but finally when this stage is done, we will be back in the driveway, okay? So if it slows down, how do we get there? Well, I'm gonna give you 3 options one more time. Pause the video, pick which one you think is right, and justify why. Go ahead. All right, so I'm guessing you probably were able to eliminate option 2, hopefully, right? Because it's slowing down. Option 2 is showing uniform motion, okay? So it's covering the same displacement each second. We know that it's changing its velocity, so by now we have an understanding that that should mean the slope of the graph is changing, it's not constant, right? For our dt graph. Okay, so we need to decide which of these, 1 or 3, is showing the speed decreasing. It's getting slower and slower, right? Well, look at option 1, right? What's happening to this slope? It's getting steeper and steeper, right? It's getting steeper and steeper in the negative direction. This thing is going further and further south each second that goes by, right? So it's not option 1. Option 3, on the other hand, shows, whoops, I shouldn't have dipped into the negatives there, shows that, right, as time goes on, it's covering a smaller and smaller displacement with each passing second compared to the previous second, right? In other words, it's getting less fast, right? It's slowing down, okay? The slope here starts out negative and fairly large, right? Fairly steep, and then it gets less and less and less steep, ending at a slope of 0. Right? Well, good, because it parks. So it's supposed to stop. It's supposed to have a velocity of 0 at the end. And we know that the slope of this tells us its velocity because d over t, rise over run, is velocity. And finally, for our velocity time graph for this portion of the journey, okay, ask yourself things like, again, what's the velocity start at? Well, it was moving south, so we know that's somewhere negative to begin with, okay? Where does its velocity end up if it parks? Right? It should have a velocity of 0 when all is said and done, right? And so our velocity should look something like that, right? It had a velocity, maybe it was, 50 kilometers per hour south, and then it gets slower and slower until it stops. Okay, this is one that trips students up sometimes. They don't like the fact that we're going up on the y-axis, but it's getting slower. But remember, right, zero, this is zero, right? This doesn't mean slower, it just means negative direction. Okay, and once again, connect this back to what we know about accelerations and velocities. We know that if something accelerates in the same direction as its velocity, it gets faster. If it accelerates in the opposite direction, it gets slower. We also know that the slope of a velocity time graph tells us the acceleration, right? Well, this is a positive slope. So this thing has a positive acceleration, but it's got a negative velocity, and so it's getting slower and slower, right? We'll explore that a bit more in the next example here, but there we go. We finished up that one, right? A completely told the journey or story of the car's journey, right? With the displacement time and velocity time graphs. Okay. So again, just a warning, right? I know we've mentioned it already, but it is a very common mistake, is assuming that a negative acceleration means you are going to slow down, right? And that a positive acceleration means you will speed up. That is definitely not true. I mean, we can see that in lots of these, right? For example, here, positive acceleration, like we were talking about, right? This is a positive slope, and the slope of a VT graph is acceleration, right? Positive slope, positive acceleration, but it's getting slower and slower. Why? Because it had a negative velocity. So a positive acceleration is kind of working against that, bringing it towards zero, right? Or here, this is a negative slope. So a negative acceleration, and it's getting faster and faster, right? So a negative acceleration does not mean the object is slowing down. It just means its velocity is changing in the negative direction, right? So that depends on whether the velocity was already negative and it's getting more and more negative, or whether the velocity was positive and it's getting less and less positive, right? For a negative acceleration, okay? If the signs of the velocity and the acceleration are the same, the object will speed up, right? The velocity and acceleration are working together, so to speak. But if the signs of the velocity and the acceleration are opposite, the object's going to slow down. The velocity and acceleration are working against each other, so to speak, right? All a negative acceleration indicates is that the object's velocity is changing in the negative direction, okay? I mean, just for example, think of a skydiver, right? Their acceleration is definitely downward, right? Which we typically define as a negative direction, but they're absolutely getting faster, right? Their velocity is just getting bigger and bigger in the negative direction. Okay, let's try one more example here together, and then it'll be your turn. So on one velocity time graph, we're going to sketch these four scenarios. I've done some color coding here. So for A, we want an object that's moving in the positive direction, okay, and accelerating in the positive direction. So if it's moving in the positive direction, that means it has a velocity that's positive, right? If it's accelerating in the positive direction, that means acceleration is also positive. So, I mean, looking at this, we know that means that it should be getting faster and faster. What's that going to look like on our graph? Well, a positive velocity on a VT graph just means our velocity is up here to begin with, right? It's in the positive velocities on the positive y-axis. If it's accelerating in the positive direction, that means it's changing in the positive direction as time goes on. The velocity is changing in the positive direction as time goes on. So we're looking for something that starts up here and continues to get more and more positive, right? So maybe, it starts there. As time goes on, the velocity gets more and more positive. Once again, remember that for a velocity time graph, right, the slope is giving us the acceleration because of this. Acceleration is change in velocity, or rise for this graph, over change in time, or run for this graph. So rise over run is change in v over change in t, which is acceleration. Well, positive slope indicates a positive acceleration here, right? And sure enough, our object is getting faster, right? Getting faster essentially means moving away from zero, right? Well, it's positive, and it's getting, since it has a positive slope, it's getting further from zero. All right, moving on to B here, an object moving in the positive direction. So its velocity is positive, but it's accelerating in the negative direction. So its acceleration is negative. Okay, so is this thing going to speed up or slow down? right? It's going to slow down, opposite signs. Its velocity is positive, but it's changing each second in the negative direction. So just to give ourselves enough room here, let's say, okay, it's starting out moving in the positive direction, but it's changing in the negative direction. So maybe 1 second later, it's only going that fast. Still moving in the positive direction, but getting slower, right? Changing in the negative direction. Okay, now notice it's never actually moving in the negative direction. To do that, it would need to have a negative velocity. Okay, so this thing is always moving forward or positive, right? It's just getting slower and slower, getting closer to zero, right? And once again, notice this is a negative slope. So since it started at a positive y value and has a negative slope, it is heading towards zero. It's getting slower, right? But that never means it's moving in the negative direction in this case here. It's just getting slower and slower. Now for C, we have an object that's moving in the negative direction and also accelerating in the negative direction. So we know both its velocity and its acceleration are negative. So it starts out, it's already moving in the negative direction, right? Its velocity is negative. Now, as time goes on, it's also accelerating in the negative direction. So if it was going -1 meter per second squared, then it's going -2, then -3, then -4, then -5. Hey, is this object, based on the graph, is it getting faster or slower? It's getting faster, right? The velocity is moving away from zero. It's just doing it in the negative direction. So it is getting faster and faster. It's just doing so in the negative direction, okay? And finally, for D here, an object moving in the negative direction and accelerating in the positive direction. So it is traveling in the negative direction, okay? But its acceleration is causing its velocity to get, less negative or more positive each second. So what does that look like on the graph? Well, it needs to be moving in the negative direction, but as time goes on, right, the velocity is changing in the positive direction. Now, it doesn't mean it's actually moving in the positive direction necessarily, right? Notice here, its velocity is always in the negatives. It's just changing towards the positives. It's getting less negative, right? Less negative. And sure enough, look at that. A positive slope, right? Positive acceleration. Since we started in the negatives and we have a positive slope, we're headed back towards a velocity of zero. In other words, we are slowing down. Okay, so we already kind of answered that as we went, but of A, B, C, and D, which are speeding up and which are slowing down? I mean, one way to look at it is speeding up means your velocity is headed, away from zero. You're going to either a bigger positive or a bigger negative. Well, we can see that A and C are doing that, right? Now, what do A and C also have in common here? We can see for A, the velocity was positive, but the acceleration was also positive. For C, the velocity was negative, the acceleration was also negative. And so just like we'd expect, they speed up, right? Their velocity is already positive and it's changing to be more and more positive each second. Or their velocity was already negative and it's changing to be more and more negative each second, getting faster and faster in the negative direction. Which are slowing down? Again, one way to look at it, since this is a velocity time graph, we know a y value of 0 means it's not moving. So if it's headed towards 0, it's getting closer and closer to being not moving. In other words, getting slower and slower. So we can see that B approaches a velocity of 0, and so does D. So those are slowing down. And sure enough, for B, it had a positive velocity, but a negative acceleration, right? For D, a negative velocity, but a positive acceleration. So its velocity was positive, but it was changing towards the negatives each second, right? So +4, +3, +2, +1. Hey, that's getting slower, right? Less and less meters per second each second. D, -4 meters per second, -3 meters per second, -2 meters per second. Always moving in the negative direction, but doing it slower and slower. All right, now it is your turn. So go ahead and pause the video and try this one out. Page 27, number 2. This is from your assignment, okay? Go ahead and, you make sure you're using your graphical analysis steps. Compare to the answer there. You can also see the solutions that are posted, okay? At the very least, do this one. But if you're wanting to get a little more practice before, coming back to the video lesson, this is also a good time to try these from your practice assignment, okay? You can wait to the end. If you want to do all your practice at once at the end, you can do that. No matter what, do this one right now. These ones, you can do them now, or you can wait till later when you're doing the full assignment. It's up to you there. Okay, and then we will move on. All right, so next we're going to talk about the concept of an instantaneous velocity or speed, okay? So if an object is moving with non-uniform motion, we know that that means its velocity is constantly changing, right? However, at any one given moment in time, it still has a specific velocity, right? For example, if you were to undergo non-uniform motion, say you were going to start at rest 0 kilometers per hour and then speed up to 100 kilometers per hour, right? Yes, your velocity was constantly changing, but at each point in time you had a specific velocity, right? You were at 0. At some point later, you were at 5 kilometers per hour. At some point later, you passed 20 kilometers per hour and 50 kilometers per hour, etc., 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 right? So even though you don't have one consistent velocity, you do have a velocity at each moment in time, right? And we call that velocity that you have at that given moment when you're undergoing an acceleration, we call that just your instantaneous velocity. It's your velocity in that one instant. Even though it's going to be different 1 second later and it was different 1 second before, we can still talk about the velocity you have in that moment. And so without learning calculus, the way we can actually find this, we're going to need a graph, okay? Because you can find an object's instantaneous velocity with a displacement time graph by using what we call the slope of the tangent. Okay, I'll talk about what that means in a second. But again, if we have a displacement time graph, we know that the slope of that graph will represent the object's velocity because of this. Again, slope is rise over run, so that's change in displacement over change in time, which is just the definition of velocity. But that idea gets a little tricky to think about when we have something like this as our displacement time graph, right? A graph for non-uniform motion. Because if I asked you to calculate the slope of this line, you would say, well, I mean, it has a different slope everywhere, right? Like if I look in this section of the graph, the slope is a lot different than the slope up here, right? The slope is constantly changing. So if I asked you to calculate the slope of this, you would say, well, it has, a million different slopes depending on where we look. Okay, which makes sense because if it has a non-uniform motion, it has a million different velocities everywhere we look. Okay, so are we out of luck? No, because it does still have, even though the slope is constantly changing, it still has a certain slope at each point, right? For example, here the slope looks something like that, right? Here the slope is a lot steeper, it looks something like that. Yes, the slope is different 1 second later, right? But at that specific moment, that's what the slope looks like. Hey, doesn't that sound similar to what we were talking about with velocities? It should, because this is a displacement time graph and its slope is the velocity, right? Even if you're changing your velocity constantly, at any one instant, you do have a defined velocity. Same thing here. Even though this has many different slopes, at any one given instant, it has a well-defined slope. And so that's where the idea of the tangent line comes in, right? A tangent line just makes contact at a single point along a line, but only touching and not intersecting. And that's actually what I was drawing here when I was showing, this kind of thing. I'm not doing a very good job, but get the rough idea, right? The slope there looks something like that. The slope there looks something like that, right? Those are tangent lines. Okay, and what they let us do is examine the slope at just one specific point on an otherwise curved graph where the slope is constantly changing. So just to kind of visualize a tangent line at different locations, right? Here's a good animation for it, right? You can see, again, this parabola has a slope that's always changing, but we can still look at like one specific point and say, okay, what's the slope look like there? Right? And then now we have a line that we can calculate the rise and run of to get the slope, right? Or, down here, the slope is pretty close to 0 there, right? If I can get it in the right spot, okay? So again, to the left of that, the slope is different. To the right of it, the slope is different. But right at that location, the slope is about 0, right? It's about a flat line. That's what a tangent does. It's a line that touches our curve at one point, okay, and then continues on. It just comes in, kisses the graph, and then moves on forever. So we use the same method, we just need a tangent line to do it because it has many different slopes. So best way to see that in action is probably with an example. This one wants us to determine the instantaneous velocity of the object 6 seconds into the graphed motion. So right here, right? At this moment, we want to know how fast it was going. A moment later, it'll be faster. A moment earlier, it was slower. We want to find the velocity right there, though, and therefore the slope of the graph at that exact location. So we want to draw our tangent line here, okay? Now, it's a little hard to show on a video lesson like this where all you can see is the screen, but in terms of like the actual how do you do this, here's my tip, okay? You're going to take your ruler and you're going to start on that side of the curve. And what you want to kind of do is just slowly shimmy it towards that point. And what I usually tell students is you want the last thing that's going to disappear under your ruler to be that point, okay? So you just shimmy it closer and closer and closer. And you can see what I want to happen is the point that I'm interested to kind of be the very last thing I can see before being covered by my ruler. That's kind of the strategy I go with, okay? So I'm going to go ahead and do that, and I'm going to draw my tangent line. And so my tangent line ended up looking something like that, right? Now, again, always a good idea, step back, and remember the point here is to represent the slope at that exact location, right? So stepping back, looking at it, I can see, yeah, that looks pretty representative of the slope there, right? It's not way off. Okay, so now, right, if I can calculate the slope of this tangent line where it's tangent to the graph right at 6 seconds, what I'll be doing is finding the velocity at that exact moment. So here we go. Let's find the rise and run of this thing, and we'll be good to go. So as always, going to try to pick two nice, easy points where I don't have to do much estimating, okay? And honestly, it actually looks like that's a pretty good point there. And hey, we might as well use that point. We know it goes through that because that's the whole thing we based our tangent on. So it looks like during that time, it runs 6 seconds, and it rises from 2 meters east to 6 meters east. So with a rise of 4 meters and a run of 6 seconds, okay, we can go ahead and calculate the slope and therefore the instantaneous velocity. So we got a rise of 4 meters during a run of 6 seconds, and that's going to give us that the instantaneous velocity is 0.67 meters per second. Okay, in this case, it's positive, so that means it's to the east. Okay, so there we go. Now again, is that its velocity the whole time? Absolutely not. Before it was slower, after it will be faster. But at that exact moment, it looks like it was moving at about 0.67 meters per second, right? And we can see that this makes sense here. We're saying that, okay, if it continued to move exactly how it was moving here, it would cover 4 meters every 6 seconds, right? Well, look, that's what we're doing. By drawing the tangent, we're kind of extending it and saying, okay, we know it changed, but what if it kept moving like this, right? It would move 4 meters every 6 seconds. All right, that's instantaneous velocity. Draw the tangent, find the slope of the tangent at the point you're interested in. All right, so as we move on to the next little section here, okay, we're going to start with just a bit of a reminder. I know, again, it's repetitive, but it's to remind you that the core principles here are always the same, right? We're connecting an equation to a characteristic of the graph, whether that's the slope, the area, or the intercept. So let's just remind ourselves, why is the slope of a displacement time graph the velocity? Well, we know that slope is just rise over run, right? Rise is how much the y variable changed by, run is how much the x variable changed by. Well, on a displacement time graph, a change in y means a change in displacement, a change in x means a change in time. And change in displacement divided by change in time, that's just the definition of velocity, right? The rate at which displacement changes. So this is the key reason why we know the slope of this graph must represent the velocity. Okay, let's do this next one here now. Why is the slope of a velocity time graph the acceleration, right? It's not just a fact to be remembered. We can show why it has to be. Now on a velocity time graph, a rise is a change in velocity, right? That's on our y-axis. And a run is a change in time. Well, now we see this is change in velocity divided by change in time, right? The rate at which velocity is changing. That is just the definition of the acceleration for an object. So again, emphasizing here, like, we're not guessing, we're not memorizing, right? Students sometimes say to me, oh, I can't keep track. How do I know if I'm supposed to do slope or area or whatever, right? And I tell them, I mean, you don't have to keep track of it. You're told. The equation tells you what you want to find, right? If we want velocity from a dt graph, well, velocity from our formula sheet is change in displacement over change in time. On a graph like this, that's rise over run. We're dividing y by x, that's the slope, right? Or similar situation here. Okay, so now remember, if we're dividing a change in y by a change in x, that's a rise over a run, that's a slope. Okay, it's asking us now, what would the area under the curve for a velocity time graph represent? So if we were in math class and I gave you this rectangle and I asked you to find its area, what would you do? Well, you'd multiply the two dimensions together, right? You'd do velocity times time. Now, apply that to the idea of a graph, a velocity time graph, right? If I asked you, okay, what's the area under this? You would take the value of the velocity, right? Maybe it's, 50 meters per second, just to put a number on it. Maybe it did that for 10 seconds. And I asked you to find this area, same thing, right? You would multiply the y value, 50, by 10, the time, 10 seconds, right? So when we're finding the area of a graph, that involves multiplying y by x, right? So on a velocity time graph, that means we're going to have y times x, okay? Or in this case, velocity times time. Okay, and so now we do what we always do, right? We ask ourselves, okay, does this mean anything, right? And there's a few ways we can approach this. One way is to think about it. We're taking how fast it was going each second and multiplying, how far it was going each second and multiplying it by how many seconds it was doing that for, right? What is that going to give us? We could also look at the units, meters per second times seconds, right? That gives us meters, so we can see this is talking about a displacement, right? And we can also relate it to the equation itself. So over here we can see velocity we know is equal to the change in displacement times the change in time. So if I rearrange this, velocity times the change in time, I get the displacement, right? Again, makes a ton of sense. How far was it going each second, right? That's its velocity, times the number of seconds it was doing that. So the area of a velocity time graph should give us its displacement. And this is the important part in showing that we understand that with our graphical analysis, right? We're not just saying, okay, we're going to find the area, because again, it's always a slope or an area or an intercept. We want to show why we need to find the area, that we understand that connection to the graph, right? But the equation tells us, we want displacement. Okay, to find displacement, I need to multiply my y variable by my x variable. When I multiply two things together, two dimensions together, I'm finding their area. Okay, so the displacement of, the area of a velocity time graph will give us the object's displacement. All right, so let's take a look at this example then. So here we have velocity as a function of time for a race car, velocity on our y-axis, time on our x-axis, and we can see that what happened here, right? Velocity on the y-axis, so we're starting out not moving, 0 meters per second, and then we steadily get faster. So we increase our velocity up to 50 meters per second, and then it looks like we move at a constant 50 meters per second for those 4 seconds there. Okay, so the first thing it asks us is to find the acceleration during the first 2 seconds. Well, we've done this quite a few times now, right? We want to, again, always same process. We have v and t, and we want to find the acceleration. Well, we know from our formula sheet that acceleration is just the change in velocity divided by the change in time. On a VT graph, that is rise over run, right? So we want to find the slope. So we just need to find the slope during these first 2 seconds. Finding 2 good points. Honestly, that beginning point and the end point for the 2 seconds there look pretty good. So let's get our rise and our run. The run we can see is 2 seconds and the rise is 50 meters per second. So using graphical analysis, we can see that the acceleration during those first 2 seconds is just going to be 50 meters per second, our rise, over 2 seconds, our run, to give us 25 meters per second squared. Okay, so now on to this one. We want to find the displacement after the full 6 seconds, okay? And again, it's nothing different in terms of our thought process here. We are given velocity and time on the graph. We want to find displacement. So v, t, and d, we want to find the formula that helps us analyze when we have those variables. And of course, it is this one, right? Velocity equals the change in displacement over the change in time. Okay, but now we're trying to find the displacement. So like we always would, let's rearrange this so that displacement is isolated. And multiplying both sides by the change in time, we get that the displacement will be equal to the velocity times the time, right? And so now for graphical analysis, we say, okay, I need to find this. What am I doing with y and x, and what does that tell me, right? Well, velocity is y, and I'm multiplying it by the change in x. Y times x, not y divided by x. I'm now trying to find the area in order to get the total displacement that's been traveled. So we need to find the area represented here. Now we got to be careful, right? This is not just a rectangle. This section here is rectangular, right? So for that part, and we can figure out the area of that pretty easily, length times width. And it actually makes a ton of sense too, right? We're saying for this portion of time, for these 4 seconds, it was moving 50 meters per second, right? And so 50 meters each second times 4 seconds will give us how far it went during that interval. But we can't just do 50 times 6. That wouldn't make sense because for this portion here, it actually wasn't going 50 meters per second that whole time, right? In fact, for most of those 2 seconds, it was going less than 50 meters per second. Only at the very end did it finally reach a velocity of 50 meters per second. And so what's really nice about this, it's a tough problem when you think about it, right? We want to know how far it went, but not only was it moving, it was changing how it's moving. So figuring out how far it went sounds like a really tough problem. But thanks to graphical analysis, it actually becomes a very simple problem to solve. We are just going to find this area, and the way that we account for the fact that most of the time it was going slower than 50 meters per second is that we are going to find the area of this triangle instead of the area of this rectangle, right? And we know that triangles is length times width, or base times height, divided by 2. And so it's that dividing by 2 that accounts for the fact that, well, for most of the time, we weren't actually going the full 50 meters per second, right? So what seems like a really complex problem actually has a very elegant solution. We're going to still just find the area of this, but it's a triangle, not a rectangle, so we'll find the area of a triangle, right? We split it up into these nice shapes that we have easy area formulas for, right? So we are going to find this total area in yellow and blue, okay? But we're going to split it up into areas that we can easily deal with, like triangle shapes and rectangle shapes. So there's our plan. We need to find the area, which is just going to give us the distance traveled, right? And it's going to be made of 2 areas. Area 1, I'm going to call it the triangle, plus area 2, the rectangle. Area of a triangle is just base times height divided by 2. Of a rectangle is just length times width, right? So now we just need to find those dimensions. Well, looking here, we've already actually got, look, our base is 2 seconds for the triangle and our height is 50 meters per second. So we're actually good to go on that one there. And then for our rectangle, we can just say, length, or the time change here is going to be 6 seconds minus 2 seconds, showing us that that is a 4-second change in time, right? And our height is really just the velocity value here. And our width, I guess you could call it too, right, is just going to be 50. So taking those dimensions and putting them in, we can say we've got 2 seconds times 50 meters per second over 2, base times height over 2, plus length times width, so 50 meters per second, times 4 seconds. And again, units are a free way to check our work, right? We can see that seconds times meters over seconds, the seconds will cancel. And same thing here, leaving us with meters. We're looking for a displacement, which is measured in meters, so that's a good sign. Doing some of the calculations, we see that it went 50 meters. So now we even know that it went 50 meters while accelerating up to its speed that it reached, right? While getting up to speed, it covered 50 meters. And then while traveling at its cruising speed, it went another 200 meters, showing us that the total displacement it would have traveled would have been 250 meters over those 6 seconds. All right. Okay, so again, key thing here, right? It's not something to memorize or just know off the top of your head, right, necessarily. The formula tells us what the area would represent, right? The formula tells us to find the area because we can see that, okay, to find displacement, I need to multiply y by x, right? Versus over here where we had to divide it, that's how we knew to find the slope when looking for the acceleration. All right, let's try one where we're now going to make, not just sketch a graph, but actually properly plot a accurately drawn graph with titles and scaling and all that stuff. All right, so an object travels at a steady 10 meters per second east for 2 seconds. The car then accelerates west at 5 meters per second squared for 4 seconds. Plot a velocity time graph. All right, before we even do that, let's just put in all our titles and everything. Okay, so I've got that all in. I'm just doing my units here for velocity. I'm going to say meters per second, and I'm going to choose to define east as the positive direction. So by saying that, what I'm now telling people reading my graph is that going that way is going further east or faster east. Going that way is going slower east or even faster west if we go down into the negatives. All right, so now before I put numbers on my axes, let's just kind of plan it out a bit, right? Always a good idea to save yourself some erasing. So an object travels at a steady 10 meters per second east, and then it accelerates west. So if that's all that happens, right? So that means the fastest, like the highest I have to go in the east is 10 meters per second, because then it's going to accelerate west. So it's actually going to get, go down on the y-axis after that. The velocity is changing towards the west. Okay, so I don't have to go higher than 10. Do I have to go down into the negatives? Well, we can kind of plan that out a little bit here too, right? If it's accelerating west at 5 meters per second squared for 4 seconds, we can kind of see that, okay, it's going to start at 10 meters per second east, then 5 meters per second east, then 0 meters per second, then -5 meters per second, then even -10, right? That's 4 seconds of a westward acceleration. So I am going to have to go down into the negatives, okay? Looks like I have to go as high as +10 and as low as -10. So I'm going to plan that out accordingly here. I'm going to make 0 kind of be right in the middle, okay? And then let's just see, we kind of want to spread things out as much as we can. Maybe if I go 5, 10, and then -5, -10, that'll work. All right, so notice I'm being consistent, right? Every square represents the same amount, okay? All right, now let's think about how far we should go for time. I have to cover the first 2 seconds and then another 4 seconds. So I've got to go up to 6 seconds minimum. Okay, I don't know if it makes sense to stretch this all the way to 6, just because then it makes the squares not be like a nice number. I think if we just go up by, I think I have 10 squares here to work with. So I think if I just go up by 1 for each tick there, that'll be pretty well spread out, right? I'm not going all the way over, but I've got more than half of the x-axis used. So let's just go up by 1s there. Okay, and now we're ready to start plotting data. I'm just going to make the 0 a little more pronounced there. Should use a ruler for that. Whoops. There we go. Okay, so the object travels at a steady 10 meters per second east for 2 seconds. So it starts out moving 10 meters per second in the positive direction, so to the east. 2 seconds later, it'll still be doing that. It's a steady 10 meters per second. So it does that for 2 seconds. Should use a ruler there as well. Okay, but then things start to change, right? Then it accelerates west at 5 meters per second squared for the next 4 seconds. So we know that that means every second its velocity is changing to the west at 5 meters per second, right? 5 meters per second each second to the west. So in this case, negative. So starting from 10 meters per second, after 1 second, a change of -5 meters per second. So still moving east, but getting slower, right? Only moving 5 meters per second east. The next second, another change of -5. So it momentarily stops, right? It's momentarily not moving, but it continues to accelerate west. So it's now going to actually turn around and start speeding up to the west. That's so far 1, 2, 3 seconds of that acceleration. We need 4 seconds, and there we go. So using a ruler to connect there, right, we can see that this is its velocity time graph, okay? And again, we know that the slope of a velocity time graph represents the acceleration. Well, sure enough, It runs 1, it rises -5. So -5 over 1 gives us an acceleration of -5 meters per second squared. Okay, so now we've plotted our VT graph, but we want to calculate the total displacement traveled using our VT graph for those full 6 seconds. Okay, so again, using the equation, right, we can see that that means multiplying y by the change in x. In other words, finding the area. Okay, so let's split this up so that we have nice, easy shapes to work with for finding our areas. I see here a rectangle. Then here I see a triangle. Now here's a common student mistake with this next one. They say, okay, well, I got this kind of shape going on, right? But do you see the problem with that? The area of that is actually infinite, right? We just stopped our graph there because we ran out of room, but like that keeps going forever. So it's always the area between our graph and the x-axis, which makes sense because that's really what our y value is referenced to, right? This -10 is -10 because it's 10 below the x-axis. So those are the 3 areas we need to find. 1 rectangle, 2 triangles. Now for this triangle, okay, this is going to have a negative area, right? We can represent this area as being negative. Remember, it's a physical quantity, right? We're representing it as an area here, but it represents a velocity times a time. Well, velocities can be negative, right? And again, that actually makes a ton of sense because during this portion here, which way was it moving? It was moving to the west, right? It had a negative velocity. So it's covering a westward displacement during this portion, right? During this time, it is moving to the west, okay? So that portion of the displacement should be negative. It should be working against this part where it was moving east. So let's find those 3 areas. So here we go. We're all set up, okay? We just need to find our dimensions now. So this rectangle, okay, the entire time it was moving 10 meters per second, right? That's like our length, so to speak. And then the width we can see is 2 seconds, 0 to 2. Then this triangle here, it's got a base or a width of another 2 seconds, right? 4 minus 2, okay? And it actually has the same height. It's also 10 meters per second, okay? So again, that accounts for the fact that it actually wasn't moving 10 meters per second. For most of that, it was going slower than 10 meters per second as it got slower and slower and slower. And finally here, right, the width of this triangle is another 2 seconds, from 4 seconds to 6 seconds. But be careful, its height is actually going to be negative 10 meters per second, right? Again, it had a negative velocity. It was moving in the negative direction there. So calculating out this total area here, you can see that we get 20 meters for this rectangle, plus 10 meters for this triangle, plus negative 10 meters for this orange triangle, right? And again, that's just saying, okay, so he traveled 20 meters there, right? Then another 10 meters while he was still moving east but getting slower. And then they actually came back 10 meters towards the west, giving us a total displacement of 20 meters, okay? And almost done, but that's a positive, and we actually know what positive means. For us, that means east. So overall, the race car ended up 20 meters east of where it started, right? Essentially, we could kind of see that from here too, right? It asked, did the object end to the east or west of where it began? We can tell that it covered more ground here than it could be undone by this, right? Essentially, these two ended up canceling each other out. And so whatever eastward displacement it built up here, it actually finished with. Okay, so last page of notes here. So I like this diagram here, this visual reminder to look for the relationships between the graphs, right? All of these are showing us motion just in terms of different variables, right? So if you look here, these are all for the same situation. It's just telling us where was an object as time went on, how fast was an object moving, the same object as that time went on. And even here we have how was that object accelerating as time went on. Okay, so notice here, right, we know that the slope of a displacement time graph gives us the velocity. So look at the relationship between the slope here and the y values here, right? Look, okay, an increasing slope, positive but increasing. Well, A positive but increasing velocity on the y-axis here. Okay, a constant positive slope for this section. Well, a constant positive velocity on the y-axis here. Then a slope that gets less and less and less steep until it reaches a slope of 0, right? And then gets steeper and steeper, but now it's a negative slope. Well, the velocity is positive, but it gets closer and closer to 0, right? 0 slope here, a velocity y value of 0, and then the slope becomes negative. Well, our velocity's y values become negative, right? And then that kind of connection, we could keep going, right? Now take that one layer deeper to the acceleration, right? Here, the velocity is constantly increasing in the positive direction. So we have a constant positive acceleration. The slope of this tells us about the y value of this, right? Then the velocity doesn't change. It stays constant, right? So a slope of 0. Well, sure enough, the acceleration is 0 for that interval. Then it actually starts accelerating in the negative direction. We have a negative slope for our velocity. Sure enough, the acceleration is constant and negative. Okay, so always kind of look at those connections between the graphs there. All right, last example, sketching our own dT/vt, and a new one for us, the acceleration time graph. But honestly, those are usually pretty simple for Physics 20 because the accelerations are always the constant, right? So a man starts at his house. He walks at a constant velocity of 1 meter per second east for 5 seconds. Then he begins accelerating at 1 meters per second squared east for 3 seconds. Okay, so I'm actually going to let's do all 3 graphs for that first section, and then we'll continue it for all 3 with that accelerated motion. So first he walks at a constant velocity of 1 meter per second to the east for 5 seconds. What's that going to look like on our displacement time graph? Well, up into 5 seconds, he should be going 1 meter each second towards the east, right? So after 1 second, he'll have gone 1 meter. After the next second, 2 meters, etc. But it's at a constant velocity, right? So we should have a constant slope here. Each second, he's going 1 meter towards the east. Okay, we'll come back to that dt graph when we go to do the accelerated motion. But let's now do the same thing for the velocity time graph. A constant velocity of 1 meter per second east for 5 seconds. What's that going to look like on a VT graph? Well, his velocity is 1 meter per second to the east, right? And that doesn't change. It's constant for 5 seconds. And now let's do the acceleration versus time graph for that section where he has a constant velocity. Well, if he has a constant velocity, what's his acceleration? Right? It's 0, right? Acceleration is the rate at which velocity changes. Well, velocity is not changing if you have a constant velocity. Another way to look at it, what's the slope of this? 0. So the slope of this should tell us the acceleration. So for 5 seconds, they have an acceleration of 0 meters per second squared. Okay, let's now continue the story on each graph for once they start accelerating. So now he's moving east already, and he accelerates to the east. So he should be getting faster and faster, right? He should now, for the next 3 seconds, be covering a greater and greater displacement each second. Okay, something like that. Just sketching, but something to show that he's getting faster and faster. Okay. Oops, messed up my colors there. Supposed to be blue for the accelerated motion. Okay. Now for the velocity time graph, if he's accelerating at 1 meter per second squared east for the next 3 seconds, well, what does that mean? He's already moving 1 meter per second to the east. Now his velocity is changing by 1 meter per second to the east for each second, right? That's what an acceleration of 1 meter per second squared means. So at 6 seconds, he'll now be going 2 meters per second to the east. At 7, 3 meters per second to the east. And finally, after 8 seconds, he'll be going 2, 3, 4 meters per second to the east, right? Because that's all that acceleration means. He's increasing his velocity to the east by 1 meter per second each second. So 1 meter per second east, 2 meters per second east, 3 meters per second east, 4 meters per second east. And finally, if his acceleration is 1 meter per second squared to the east, how do we show that on the graph of acceleration versus time? Well, he didn't have an acceleration, and then he suddenly does have an acceleration, right? Now, truth be told, it's not possible to like instantly be accelerating at 1 meter per second squared. There'd be a little time where it was, building up to that. But based on what we have here, the best representation we can do is something like this, right? A little jump up, and then he accelerates at 1 meter per second each second for 3 seconds. Okay, now again, notice constant positive slope. In fact, a constant positive slope of 1 meter per second each second, right? Well, look at this. The slope of this tells us the y value of our AT graph. Positive constant 1 meter per second each second. And there we go. That is it for the notes and examples portion of chapter 1, lesson 3. Okay, so now you are finished the lesson. It is time to go do your practice, but start out with this one here. This is a good one for kind of where you are and what's fresh in your brain right now. But after that, you can go and you can finish up the remaining practice problems for this lesson, okay? Make sure you are doing that practice. It is important. It is expected that you're doing it. Again, you wouldn't want the first time you kick a soccer ball for yourself to be during the game, right? You want to build those skills beforehand. Okay, so the same goes for physics. You can watch someone else do it, and that is helpful, but ultimately the real learning starts when you're the one doing it on your own. So try those ones out, okay? Make sure for any that you need some clarification on or some help with, you're reaching out, booking an meeting, sending an email, whatever it might be. I'm always happy to help. All right.